In this video, we're covering section 6.3, calculating probabilities of events. So we are going to look first at probability with equally likely outcomes. So let S be a sample space consisting of n equally likely outcomes, and E be any event then if the number of outcomes, in our event is the number of outcomes in our sample space. And this is something you're familiar with. Okay, if we roll a standard die, what's the probability that I get a 3? Well, there's 1 3 out of 6 total options. What's the probability that I get an even number? Well, there's 3 evens out of 6 total. That's all we're talking about. Number of outcomes in our event here was 1 or 3 out of the total possible. So we'll start off with things fairly familiar. An urn containing 8 white balls and 2 green balls. A sample of 3 balls is selected at random. What is the probability that the sample contains only white balls? Well, there are 8 white balls total. So what we are going to do is we're going to do how many ways can we choose 3 balls from 8? Okay, so 3 out of the 8 white balls divided by how many balls total? Well, there's 10 total, so 10 choose 3. Okay, so a little bit more complicated than just calculating a dice roll or a die roll. However, it's the same probability. This is the number of ways we could select 3 out of 8 white balls, and here 3 out of 10. So we've got, this is 56 over 120, which is 7/15. So that's part A. Part B, what's the probability at least one green sphere? So what that means is we're going to have 1 green, or we could have 2 green. We only have 2 green spheres, so that's all. We can't have 3. So what we are going to do is we're going to figure out how many different ways we could choose 1 green sphere out of the 10. So this is 2 choose 1 for the green sphere, but then we need to combine that with 8 choose 2 for the 2 other spheres we choose that will be white. Okay, so this is 1 green and this is 2 white. And then we have to add to that all the probabilities of getting 2 green spheres, so that's 2 choose 2 times 8 choose 1. Now, because we don't need all 3, we only have 1 sphere left to choose. Okay, so if we calculate this, this is 2 times 28 plus 1 times 8 equals 64. So this is the numerator. There are 64 different ways to select at least 1 green sphere, and we're going to put that over the 120, which gives us 8/15. So we're still going to have to use our combinations, maybe sometimes permutations, to figure out these numerators and denominators. So as we do more examples, we'll get more comfortable with that. Quality control. Toy manufacturer inspects boxes of toys before shipment. Each box contains 10 toys. The inspection procedure consists of randomly selecting 3 toys from the box. If any are defective, the box is not shipped. Suppose that a given box has 2 defective toys. What is the probability that it will be shipped? Okay, so probability that it will be shipped means that we chose 3 and all 3 of them were working properly. So we have 2 defective and 8 ones working properly. So that means we had 8 choose 3 over 10 choose 3. And notice this is the same probability as up here, 7/15. So that's approximately 0.47. So there's a 47% chance that it gets shipped with 2 defective toys. That's almost half. They need to change their quality control. Example 3. A professor is randomly choosing a group of 3 students to do an oral presentation. In her class of 10 students, 2 are on the debate team. What is the chance that the professor chooses at least one of the debaters for the group? Okay, so at least one. So we need to look at the probability of one debater and add that probability that she chooses both debaters. Okay, so out of the 10 students, 8 are non-debaters and 2 are debaters. So if I have one debater, that means I'm going to do 2 choose 1 times 8 choose 1 plus, sorry, this should be 8 choose 2 because there are 3 members to do a presentation. Then we have 2 choose 2 because we're choosing both debaters times 8 choose 1 for the one non-debater that's chosen. Now, this calculation looks a lot like the one we had up here. 2 choose 1 times 8 choose 2. Yep, same answers. And we have 10 choose 3 again on the bottom. So we've already done these calculations. This is 8/15, which is approximately 53%. So over half that at least one of the debaters will be on that presentation group. Okay, example 4, medical screening. Suppose that a cruise ship returns to the United States from the Far East. Unknown to anyone, 4 of its 600 passengers have contracted a rare disease. Suppose that the Public Health Service screens 20 passengers selected at random to see whether the disease is present aboard ship. What's the probability that the presence of the disease will escape detection? So we have 4 that are ill, and we have 596 healthy. So what's the probability that the presence of the disease will escape detection? That means we have 596 choose 20 divided by 600 choose 20. And that is approximately 0.87 or 87% chance that they will not catch that illness. That they will not catch that the illness is coming aboard or coming to the land. Example 5, rolling a die 5 times. A die is rolled 5 times. What is the probability of it attaining exactly 3 fours? All right, so total number of combinations is, well, 6 for the first, 6 for the second, 6. So we have 6 to the 5th power for the total number of outcomes. Now what we're going to do is we are going to look at the 3 fours. Exactly 3 fours. That means there are 5 choose 3 ways to choose 3 of the 5 rolls to get a 4. So this is the number of fours rolled and how they appear. Okay, so for example, 1, 2, 3, 4, 5. My 4 could be the first 3. It could be this one, and this one. It could be this one, and this one. So we're looking at all the different ways we could choose the fours to be within this roll of 5. And then we're going to multiply that by The other options don't matter. So 5 times 5, not 6, because I don't want it to roll a 4. That would be greater than 3. And so this is my calculation. If I plug that in, let's see, that gives me 7776 on the bottom, and then 10 times 5, which is about 3% chance of obtaining 3 4s in 5 rolls of a die. Now let's take a look at the complement rule. The complement rule states that the probability of an event E to the probability of its complement, E complement. When applied together with counting techniques, it often simplifies computations of probabilities. So we've done this before, where we recognize that something not happening is the opposite, so we do 100% minus. For example, if there's a 72% chance that I will not have breakfast tomorrow, then there would be a 28% chance that I have breakfast tomorrow, because they need to add up to 100. So the famous birthday problem. A group of 5 people is to be selected at random. What is the probability that 2 or more of them have the same birthday? All right, now to simplify this a little bit, we're going to ignore leap day, and we're going to assume that every day of the year has an equal likelihood of occurring. Not precisely true, but close enough for our purposes here. So in the denominator, we're going to have 365 options for the first person, times 365 options for the second, times 365 options again, so for all of these. So that's going to be 365 to the 5th power. Now, if we were try to figure out that the probability that 2 or more of them have the same birthday, that could be rather cumbersome, rather difficult. It might be easier for us to calculate that they all have different birthdays. Okay, and then we'll do 1 minus the probability of that happening, and that will tell us what's the likelihood of them sharing, at least 2 of them sharing a birthday. So let's have the probability that they all have different birthdays. Well, that's going to be 365 options for the first, 364 options for the second, 363 options for the third, 362 options for the fourth, and 361 options for the fifth. So if we calculate that, that's going to be approximately 0.973, or about 97% chance that they all have different birthdays. So 1 minus the 97, 0.97, 0.03. So a 3% chance, it's actually closer to 2.7% chance that 2 or more share a same birthday. And that finishes our notes for section 6.3. Thank you for watching.